Okay, welcome back to Number Sense Academy, and today we're going to be talking about linear equations. So let's get right into it. Um, linear linear equations. Very important topic. So the first thing we want to look at, what does it mean to be linear? Well, if you look at the root word of linear, right, we get line. Okay, so when something is linear, it pertains to a line. So linear equations has the characteristics of a line. So a line is, or a linear equation, if you want to call it that way, or a line. Um, it is it is a curve. A line is a curve. So it's part of the family of curves, but it has very specific properties that separates it from other curves. One, lines are straight. Okay, they're straight lines, and they don't have endpoints. Okay, so you draw a line, they go on forever, and we use arrows to indicate that the line goes on forever. So here I have a line, and when I put arrows at the end, that means it goes forever in this direction, right? And it also goes on to infinity or forever in that direction. So it has no endpoints. If you have a line that has endpoints, let's say maybe look something like that, so that means it's terminating. I normally put these caps or stumps to show that it is terminating. This is actually called a line segment. So it means it's just a piece of a line. It's a segment of a line. But typically lines go on forever. Okay? On this line, because it goes on forever, there are infinite points. Infinite number of points on the line. So if I take a line and I draw it out, I could find these different points, and there's an infinite number of points on these lines. So I could draw as many of these points as I want on this line, and I can never cover it up until we start overlaying them on top of each other, right? Infinite number, and then the longer I draw this line is the more points that become available. Okay, so there's an infinite number of points on the line. Another property of lines, we can see that they have direction. Okay, so in this case, it's going right to left, but they could go in all sorts of directions, right? It could be diagonal up, diagonal down, uh, vertical up and down, horizontal up and down, and they could occupy all sorts of angles. So this is direction. But you also notice as I'm drawing these different variations, you notice something that they have some sort of steepness, right? So this line, it's relatively steep compared to what? You have to compare it to something. So this one is steep going up. This one is steep coming down. This one is straight up and down. This one has no steepness. So it's flat. This vertical one is hard to define. This flat one is easy to define. There is no steepness. And then we have these two, which are steep, but to what degree? And we'll get into that a bit later. Okay, so more about lines. To represent lines, we represent lines using equations, hence linear equations. And the equations tell us about the steepness of the line, and it tells you about the direction of the line. All right, so the equations, just by looking at the equation, you can determine the steepness, and we call this slope, right? And we can determine the direction. So typically there's two directions. Either it slopes up to the right, or slopes down to the right. And with steepness, we could talk about flat versus, say, very steep. And I'm going to throw this in here. So steep that you can't define it, that it is undefined. And we'll get into that as well. Okay. So what's the definition for a line? So let's come up with a formal definition. All right? Or a definition of a linear equation. So an equation is called linear if each term in the equation only contains one variable and each variable has at most a power of 1 or a constant. What does this mean? So let's look at some examples to clarify this. Example 1. So if I have x plus y, and that's equal to 2, then we have 3 terms. So this is term 1, term 2, and term 3. So these are the 3 terms. When we look at this term, there is only, it only has one variable. When I say one variable, so we normally write these as a product. So this has one variable. This has one variable. And this is a constant. Now, if we look at the power that's associated with each of these ones, remember, anything that's raised to 1 is just itself. So a to the power of 1 is just a, which means that we could assume that because this is x and this is y and this is 2, they're all raised to the power of 1. So there's a 1 here, there's a 1 here, and there's a 1 here. So the biggest power is 1. So this checks, by definition, it meets the criteria of a line. Okay, let's look at another example. So what if I have 2x plus 3y minus 5 equals 0? So again, we have 3 terms. We have term 1, term 2, and term 3. We'll ignore that one. or we'll ignore the 0. So for term 1, we have one variable. So there's one variable. For term 2, we have one variable. And then for term 3, we have a constant. And if we check the power, then we see that there's a 1 here, a 1 here, a 1 here. When for the term that's attached to the variable, we don't care because that could also have a different power, so to speak. And then what I mean by that is, what if I had 4x? This x has a power of 1, but this 2 can be written as, this 4 can be written as 2 to the power of 2, x to the 1. But we don't care about this. All we care about is what the variable is, because that's what we're going to change. We could change the variable. We're not going to change the constant, even if we could write it as a power. We're not going to change it. But we could change the outcome of the variable. If it's x squared and we change the x value, we're going to get a certain value for x. Okay. All right, let's look at another example. So suppose I have 2xy plus 3x is equal to 5. So I have my first term, my second term, my third term. So let's work, I'm going to work from the left, or from the right to the left. So this one is a constant. There's a power of 1. I have, this one has one variable. We don't care about the coefficient. There's a power of 1. This one, there are 2 variables. This does not check. Even though each variable has a power of 1, the overall degree of this term is 2. Because the 1 plus 1 is part of this term. So we have 2 degrees. So this is of degree 2. All lines have terms with degree 1. And degree 1 just means the total number of exponents that's attached to each term. All right. So that's good there. So as we continue with linear equations, there's some properties that you need to have. There are 3 ways of writing linear equations. So linear equations can be written in 3 ways. The first way is what we call standard form. Standard form, or general notation, or general form. And what that looks like, it's a to the x plus by plus c equals 0. And a, b, c are constants. If they're not constants, then we're in a situation where the degree of each term is more than 1. So a has to be a constant, it has to be a number or a fraction or an integer, whatever you want. This has to be a constant, and c has to be a constant. So that's one way of writing it. The second way of writing it is what we call point slope form. And it looks like y minus y1 equals m times x minus x1. And y1, or I should write it as x1, and y1 is a point. So it's a coordinate. And then we have y, the x, and m. M is what we call a parameter, and we'll get into that. And then we have y, which is the dependent variable, and then x, which is the independent variable. And then y1 and x1 are just some point. So this equation kind of, it's self-explanatory. There's a slope and there's a point. So it's point slope form. So that's pretty self-explanatory. The third way is what we call slope intercept form. And this, in my opinion, is the most valuable form. And it's simply y equals mx plus b. Now with point slope form, it's a transition to get to slope intercept. And we'll look at some examples in another video of what that means. But y equals mx plus b, there's a lot of value here. Now, each of them have their own advantages, of course. But this one tells me, in my opinion, everything I need to know about a line. And if you understand what's going on here, you could actually look at an equation and discuss it without even graphing it. You could talk it through. You could talk about solutions. You could talk about what everything means. And you don't even have to discuss it. Right, so I'm going to take a deep dive into y equals mx plus b. All right, so let's do that. So here we have 4 variables in this equation. Well, really and truly, there's only 2 variables. The only thing that's allowed to change is y and x. M and b are what we call parameters. Okay, so parameters. These parameters, this is what differentiates lines. Right, so every equation is going to have a y written there and it's going to have an x, but what's going to be different is m is going to be different and b is going to be different. So it tells you the different types of lines. And given these values, we could make assumptions and draw comparisons between other lines as well. All right, so let's talk about what all these things mean. So we have y equals mx plus b. So what is m? M is the slope. The slope is another term for steepness. So think about climbing up a hill. If you're climbing up a mountain and you're going up the side of a mountain, that's going to have a slope. And it could be really steep or it could not be steep at all. Or if you're walking on the road, that doesn't have any slope because it's just flat, unless you're going up a hill. So the m is the slope. What it also tells you, it tells you the direction. All right. Then we have b. B is called the y intercept. And this is a value that lies on the y-axis. So it lies on the y-axis. And it has a coordinate of 0 and b. Why is that? So if I draw this line real quick, so this is my y-axis, this is my x-axis, this is my origin. So the y-axis, there's a bunch of points along the y-axis. It runs up and down. Okay, so y-intercept means that the line crosses this y-axis. This is where the line crosses this y-axis. So if I write it as such, and it's crossing the y-axis here, every single point on the y-axis has an x value of 0, because if I'm counting in the direction of x, and I start from this side, and I go over to this side, when I get here, as I approach this line, I get to the origin, which is 0, 0, and that's equal to 0. Okay, so that's some properties about M, the slope, and B. Actually, I want to do one more thing about M. So, or let's continue with this discussion. So M, we know it's a slope. It's essentially rise over run. So it's a ratio of the rise versus the run. Right? So this tells me how fast is the upward change. All right? And then the run tells me how fast is the horizontal change. How fast is the upward change versus how fast is the horizontal change? So if I have a really steep line, then I'm not gonna put it on the plane, I'm just gonna draw it. So if I have this line, right, and I pick 2 points. So I'm here and I want to get to here. So to get to here, essentially what I'm doing, I have to go up and forward, or I have to go forward and up, even though I might literally just be sitting on this diagonal. But essentially what I'm doing, I'm going this way and then I'm going up. And if I want to go to another point, say I want to get to here, I got to go this way, then I got to go up. So it looks as though and even though this is not a scale drawing, it looks as though I'm going as far up as I'm going forward. Now, what if I was to look at this example? If I want to change points, if I want to go from this point to this point, I'm going to take a small step forward and then a big step upward. So this rise, so if I go back to this one, this rise is equal to the run. Approximately. We're going to say it's about equal to the run. In this case, the rise is much greater than the run. Okay? So, and another example, if I was to do this, and I want to go from this point to this point, then because it's sort of flat or it's not as inclined, I'm going to do a lot of horizontal movement and then a small amount of vertical movement. So this is telling me that the rise is less than the run. Now let's put this into sort of mathematical terms so we could reason out, just by looking at the equation, what's happening with the rise versus run. So if the rise is equal to the run, right, then I'm probably going to have something that's close to 1 ratio-wise. So what's close to 1? So if I take 1 step up, 1 step forward, right, so that's equal to 1. Okay, so in this case, the rise is equal to the run. It doesn't matter if it's 4 over 4, 4 steps to the right, 4 steps up. It's just 4 over 4 is the same as 1 over 1. All right, now look for this one. If I'm rising greater than the run, so I might have something like, let's see, 1, and then this looks like 4. So I have 4 over 1, right? This is the rise over the run. Now here, I have something that looks like, if I say this is 1, say that's 1, then this looks like 3. So I have a rise of 1 and a run of 3, right? This is the rise over the run. Now, if I compare these two, this is basically a whole number, right? This is a whole number. 4 over 1 is 4. So what this tells me is that whole numbers tend to be steeper. So whole, or no, and I say whole numbers, I also, maybe I shouldn't say whole numbers. Integer values, because they can be integers. Integer values are steeper, or represent steeper slope. Okay? And then fraction values have less steeper slopes. All right? So let's take this thought and then let's come up with some general terms. So if you're dealing with the slope, so it's rise over run. If you're dealing with the slope, and if m, so this is the slope, right? M is rise over run. So if m is greater than 1, meaning that the top is bigger than the bottom, the rise is more than the run, then the line is steep. Now, very steep will compare to, like if you want to compare very steep, then you have to compare it to the x and y axis. And what I mean, because, for example, that's steep, but that's steeper. And then this is even steeper. Okay, so you need really big values of m to make it steep. So we could also add to it that as m gets bigger or larger, then the line gets steeper. Now we have to think of this from another angle as well. So this is for lines that are going up to the right. So this is for positive lines. So true for positive slope. The other rule is if m is less than -1, then we could say the line is steep. Okay? And I'm saying less than or equal to 1 because less than 1, but it could be equal to 1, but it's steep. And as m gets smaller, the line gets steeper. And this is true for negative slope. Okay? Now, so these are for steep lines. Let's look at another scenario. So again, we know that m is the rise over run. So remember from the first example where the sort of flatter line was a fraction? So we're going to come up with a general rule then that if m is between -1 and +1, then the line is, let's say, flatter. Okay. Now I'm going to throw this in there because for the line to be completely flat, if m equals to 0, the line is completely flat. If m equals 0, the line is completely flat, This is going to be a very important point in some other scenarios. So when I'm saying between -1, any number between -1 and 1 is a fraction. So I'm going to write that just so we don't forget. A number between -1 and 1, as long as the number is not 0, then that number is a fraction. Okay, so I'll do a quick graph here so we can see quick graphic. So I have y and x. So if I have a line that say looks like this, perhaps it's getting a little bit flatter. I could have one that looks like this, right? That's even more flat than that one. So it's getting more angled towards the x-axis, like it's getting rotated into the x-axis. So these slope values are between 0 and 1. And then you might have something that completely sits on the x-axis, or it's flat, but it goes through another point, and now it becomes completely parallel to the x-axis. So when the slope is 0, that is a parallel line to the x-axis. And let me write that somewhere so we don't forget. So I'm going to just write it. When m equals 0, the line is parallel to the x-axis. Now there's another situation that we have to mention that's very important. What if you have so we have y and x. What if you have a line that looks like this? So this is my line. Call it L1. What if you have a line that looks like that? This slope m is undefined. Like we don't know how this is just a falling off a cliff. It doesn't have a slope. It's just as steep as it gets. Okay? And you notice that when m is undefined, the line is parallel to the y-axis. All right? So these are things that you can keep in mind about the slope. Okay, so let's I'm going to put up some examples, and then so we could kind of solidify what we talked about today or so far. So if we have 3x minus 2y minus 12 equals 0, what can we deduce about this? Well, one, the equation is in standard form or general form. We know it's a line. Okay, so we can make that right away because every single variable has only exponent 1, and there's only one variable per term. So we know that it's a line. So those are the two things we know. But we can't really speak about the slope because we don't have enough information. Or we have the information, but we need to put in a form that we can understand it. So just for now, I'm just going to do some quick manipulation to get this into slope-intercept form. So what we're trying to do now, we're going to isolate y. And if you need to learn how to work with or solve for a certain variable, then there's another video that you can check out. But we need to put this equation to slope-intercept form. All right, and it's pretty straightforward. So I'm going to isolate for y. So how am I going to do that? So since there's a negative 2y on this side, I'm going to bring it to the other side. So I have 3x minus 12 equals 2y. But I could also, because it's an equation, I could write it as 2y equals 3x minus 12. And then I need to get y by itself because it's 2y, not y. I want y. I don't want 2y. So now I have to divide everything by 2. So 2y over 2 is equal to 3x over 2 minus 12 over 2. And these cancel, so I have y equals 3 over 2x minus 6. Okay, so let's pull this apart. So the first thing I notice is that the y-intercept is negative 6. So that coordinate is going to be 0, x is 0, and negative 6. So I could find that point. So this is where the line crosses the x-axis. The slope, on the other hand, is equal to 3 over 2. And I notice that the 3 is greater than 2. So this line, this is a pretty steep line. Also, this 3 over 2 is positive, so it slopes up to the right. All right, so I'm able to deduce all those things. I have the direction, the steepness, and I know where it crosses the y-axis. Okay, let's look at another example. If I have negative y is equal to 5 minus x, again, this sort of looks like it's in slope-intercept form, but I'm going to convert to slope-intercept. This is a negative y. That's not slope-intercept. So again, I'm going to do a bit of configuration or a bit of manipulation. So I'm going to bring the y to the other side. So I have, I'm going to switch sides with these values. Or I'm just going to divide by negative 1. Let's just divide by negative 1. Okay, so you have to be able to determine that as well. You could just move things around until you get what you want. So if I divide by negative 1, this becomes positive y, this becomes negative 5, and this becomes positive x. So slope-intercept form, I'm going to write it as x minus 5. All right, so what do we got? So we know that b, the y-intercept, is equal to negative 5, and that coordinate is 0, negative 5. And then the slope, remember, any number multiplied by itself is itself. So the slope is 1. Same as 1 over 1. Okay, so in this case, the rise is equal to the run. So it's not that it's not steep, it's like a 45-degree angle. So it's pretty balanced. We can leave it as that. So if we had another equation to compare it to, like say if we want to compare it to the previous example, then the previous example has a steeper line than this one, because that's 3 over 2 and this is 1 over 1. Okay, look at another example. So if I have 1/3 x minus y equals negative 2, then this becomes, I'm going to convert it to slope-intercept form. So if I bring the y to this side, then I'll bring the 2 to that side. I'm going to end up with 1/3 x plus 2 equals y. So y is equal to 1/3 x plus 2. And this is in slope-intercept form. So again, we know that the y-intercept is 0, 2. right? No need to spend much time there. But the slope is 1 over 3. So the rise is less than the run. So we're running further than we are rising. So in this case, this line is less steep than the previous example where that was 1. So this is less steep. So it's closer to flat. And we also know that it is a positive slope, meaning it goes up to the right. All right, look at another example. So if I have negative 3x minus 2y equals 9. So if I solve, I'm going to convert to slope-intercept form. So I end up with, I'm going to bring this over here and bring that over there. So I have negative 3x minus 9 equals 2y. So 2y equals negative 3x minus 9. Then divide everything by 2. Okay, so I have y is equal to negative 3 over 2x minus 9 over 2. So 9 over 2 is equal to 4.5, but we could keep it as 9 over 2, right? So now let's speak about this. So we know that the y-intercept is 0, 9 over 2, or you could write as 0, 4.5 if you like, if that's easy to understand. But then we have a slope that is negative 3 over 2, okay? So just looking at, if we ignore the negative sign, we can say the rise is greater than the run, right? So it's steep. And not just that it's steep, it slopes down to the right because of the negative slope. Okay? All right, another example. So suppose I have y is equal to 5. Now, this is interesting, and I want you to think about this. If y is equal to 5, if I want my equation to be in y is equal to mx plus b, I know that b is equal to 5 because b is always the constant. The number that has the x behind it, that's where I get the slope from. If there's no x, there's no slope. So there's no slope in this equation. So this equation, or this b, is 5. So my y-intercept is 0, 5. The only way that, what this is telling me then, if I only have the y-intercept, this is telling me that m is equal to 0. So for y equals 5, m is equal to 0. And remember that m is always attached to the x. So I could actually write this y equation, or this y equals 5, I could write it as y is equal to 0x plus 5. And remember what I said before. When m equals 0, the slope is flat. Slope is flat. And what does that look like? When m equals, if the slope is flat, that means it's completely flat, then what we end up with is a line that is parallel to the x-axis. So what I do, I locate, so there's 1, 2, 3, 4, 5. So I find 0, 5. I find 0, 5, and I just draw a line to that point, parallel to the x-axis. Now I know I didn't do that for the other equation, but I just wanted to make it clear that if y is equal to a constant for your equation, it's just a line through the intercept. So find the intercept and then draw a straight line parallel to the x-axis through that. You can make it as long as you want. I normally encourage students to make it just the same length as the x-axis if you want. You can make it shorter. As long as you put your arrows on either end, then we know that it's continuous or that it goes on forever. All right, one last example. What if I have x is equal to 4 or negative 4? Okay, so this is pretty straightforward. There is no y value. The slope is not defined. Like we're not telling you what the slope is. Remember, x doesn't mean the slope. It's the number that's in front of the x that means the slope. But you can't have it if there's no y value. These two have to work together. If there's no y value in the equation, then we can't define the slope. Okay? So the slope is not defined. This simply means that all we have is a line. So if I go -1, -2, -3, -4, and I locate this point, what I have is a line that goes through that point and it's parallel to the y-axis. So that's all you can do for this. All you can do for this is find the point on the y-axis. So it says x equals 4, so find x equals 4, and then draw a vertical line that's parallel to the y-axis. And that's it. And that's your intro to linear systems or linear equations. It's not linear system, just linear equations. We'll get into some more stuff later on. Lots more to come.